So a very good afternoon to all of you. So I welcome you all in this live tutorial session number 6, and hope you all have completed till the assignment number 5 and you have performed well. And so let us begin this first problem of today's session. So the first question is, the flyback converter has an input of 44 volt and output of 3 volt, a duty ratio of 0.32, and switching frequency is 300 kilohertz. The load resistance is 1 ohm. Determine the transfer turns ratio such that the minimum inductor current is 40% of the average. So you can try it, and this question is based on the last tutorial. Also we have discussed about the flyback converter. So if I have gone through the last tutorial session, you might have known the relation between output voltage, input voltage, and duty ratio for the flyback converter. In this question, what we have given input voltage 44 volt and output voltage as 3 volt, and duty ratio is 0.32, and switching frequency is given as 300 kilohertz. So for flyback converter, we see the relation between in continuous conduction mode, V0 divided by Vin is equal to D1 minus D into N1. So you have to find out this transfer turns ratio N2 divided by N1. So put these values and you will get the answer. V0 3 divided by 44 volt, D is given as 0.32, 1 minus D comes out to be 0.68 into N2 divided by N1. So turns ratio will comes out to be 0.145. So the answer will be D. Now let us see the next problem. For both single phase and three phase control rectifier, delay in alpha creates a phase displacement of the phase current with respect to the phase voltage equal to alpha. The cosine of this angle is.
Sir, can you show the last slide, please, sir, once?
Okay. See.
Thank you, sir. Thank you, sir. I've written, sir.
Okay. So here alpha is this. Alpha denote the firing angle. So anyone knows the answer for this question? You can type your answer in the chat box. So if you compare single phase full bridge control rectifier with the three phase full bridge control rectifier, so if you draw the waveform of source current for ripple free output current for constant load current, then you will get the waveform like this. And for three phase control rectifier, each supply or each phase will conduct for the angle of 240 degree. So you can make waveform like this, and I naught minus I naught in the load constant load current. So here we have the firing angle, and this one is pi plus alpha, and then we have 2 pi plus alpha. So accordingly, if you write the Fourier series for this source current, then it comes out to be IST summation of only odd harmonic terms will be there 135, it goes up to infinity, and 4 I naught divided by n pi sine n omega naught t minus n alpha. So if you write the fundamental term only, then is1t comes out to 4 I naught divided pi sine omega naught t minus alpha. And if you write this RMS value is1, then it comes out is1 for I naught peak value divided by root 2. So you can write it as 2 root 2 I naught divided by pi. So and the RMS value of whole source current will be equal to the load current, output load current. So you can write this distortion factor is the RMS value of the fundamental current divided by the RMS value of the source current, whole source current. So it comes out to be 2 root 2 divided by pi. It is coming as constant value. From here you can find out the THD coming out to be 1 divided by G square minus 1. So it is 48.34%. So it is irrespective of this firing angle, it is always constant. And if you go to find out the input power factor, then it will be G into fundamental displacement factor. So for how fundamental displacement factor is the cos alpha, because if you see this fundamental current with respect to the voltage, then the displacement will be the alpha term. So in this question it is asking about this only. And if you write for 3-phase full bridge control rectifier, you can write the IS1T for I naught divided by n is equal to 6k plus minus 1 infinity for I naught divided by n pi sin n pi divided by 3 sin n omega t minus n alpha. So again, this one be not fundamental, whole the Fourier series of whole source current. From here you can write IS1T, that comes out to be 4 I naught divided by pi sin 60 degrees sin pi by 3 sin omega t minus alpha. So here also you can see that displacement, the angle between the fundamental source current and the voltage is the alpha, that is firing angle delay. So you can write fundamental displacement factor as cos alpha. And in this, if you want to find out this distortion factor, then IS1 divided by IS, so it comes out to be 3 divided by pi. And if you THD, you can find from here, you can find out that, and input power factor will be G into fundamental displacement power factor. So 3 divided by pi into cos alpha. So what will be the answer for this question? It is the power factor of first harmonic, that is the fundamental component. So the B is the correct answer. Now let us see the next problem. So an industrial site has a constant power demand of 100 kilowatt over a year of energy consumption. Compute the customer load factor over 1 year of providing energy to this site. So this question is related to power system. So if you know the load factor formula, you can compute. Let me give you a hint. The load factor, you can write it as the average load divided by peak load. It is the ratio of average load over a designated period of time to the peak load occurring on that period. So you can try this question yourself. You can type your answer in the chat box. Here the average and peak demand is the same, because it is written as it is a constant power demand of 100 kilowatt over a year. So the average demand and peak demand will be same. So what will be the answer for this question? Chandan Verma just replied A. So if you want to write the annual load factor, then how you can write it as here it is asking about the load factor over 1 year. So annual load factor will be total annual energy divided by annual peak load, means peak load occurring during that time, during over that period, peak load that is given in watt. So you have to multiply it with hours. Then how many hours in a year? 8760 hours. So total annual energy you can find like total annual energy will be, it is given as constant power demand of 100 kilowatt into how many hours in a year? 8760 hour per year. So 876 kilowatt per year, and we have annual peak load is also same, $100 kilowatt. So this is because the power demand is constant, the average and peak is the same. Average and peak value of power is same. So you can write annual load factor 876,000 kilowatt hour per year divided by 1000 kilowatt into 8760 hour per year. So it comes out to be 1.0, or you can say it as 100%. So the correct answer will be A. Chandan has given the correct answer. Now let us see the next problem. Next problem is that Clarke transformation in synchronous machine analysis is well known from. First option is 2-phase to 3-phase transformation. B option is 3-phase to 2-phase transformation. C option is 2-phase to 2-phase transformation. D option is 3-phase to 2-phase transformation. I think you all are familiar with this transformation theory, ABC to alpha beta to DQ transformation. So this question is related to that part. You can try yourself and answer, type your answer in the chat box. Sorry. Okay, I got one answer. Okay, two options are same here. This might be, so I change this option, 3-phase transformation. Now it is okay. Okay, I got some of the responses. So if we see the natural ABC frame, ABC domain to alpha beta domain, then B went to DQ. So this part is called Clarke transformation and this part is Park transformation. So we can say it as 3-phase AC, we can say it as 2-phase AC, and this we can call it as DC. So alpha beta, you can also say that it is 2-phase orthogonal stationary reference frame. And DQ can say it as orthogonal rotating reference frame, and this one is natural reference frame. And the correct option is B. So let us see this fifth number question. So assume a residential house load, total load is 7.5 kilowatt from 11 pm to 8 am and 15 kilowatt for the remaining 24 hours. Determine the total kilowatt hour energy consumption for 24 hours. This type of question we have covered in the last tutorial session, so you may be able to solve this type of question. You can try it. If you have any query in this question we are solving, you can ask in between. You can solve parallelly with me. The load is 7.5 kilowatt for 9 hours from 11 p.m. to 8 a.m. and 15 kilowatt for the 15 hours for 15 hours, that is 8 a.m. to 11 p.m. So we can write it as the total kilowatt hour energy consumption for 24 hours will be, so 7.5 kilowatt for 9 hours. You can multiply it with 9 plus 15 kilowatt hour for 15 hours, then we will get it as 67.5 kilowatt hour plus 225 kilowatt hour, so 292.5 kilowatt hour. If the electricity price rate is given, then you can find out the total electricity price for that energy consumption. So the answer for this question will be D, 292.5 kilowatt hour. So let us see this 6th number question. A solar PV system is designed to process 1000 kilowatt of power at 460 volt at 460 volt 60 hertz 3 phase AC. Anyone have any query? At 460 volt 60 hertz 3 phase AC with an amplitude your voice is cracking. Brinda, your voice is not able to, I am not able to hear you. You can type your query in the chat box also. With an amplitude modulation index of 0.85, determine the input DC voltage for 3-phase inverter. So these are the options for this question number 6. So if you see the relation between amplitude modulation index with the phase voltage and the DC voltage, it will be like that: phase peak value, you can write amplitude modulation index MA into VDC divided by 2 for 3-phase inverter. So using this formula we can get the input DC voltage for 3-phase inverter. So V phase peak will be we have given the, it is line to line 460 volt is the line to line voltage given. So first compute this into peak value, and then for phase value you should divide it by √3. So, and we have amplitude modulation index of 0.85 into VDC divided by 2. So VDC will be 460 into √2 into 2 divided by √3 into 0.85. So it is coming out to be 883.7 volt, so approximately equal to 884 volt. So the correct answer will be B, 884 volt. I will give you some time for writing if you want before going to the next question. So now let us see the next problem. Two similar PV modules are subjected to the same irradiance and temperature. The short circuit current output of the first module is 3 ampere and open circuit voltage output is 18 volt. The short circuit current output of the second module is 3 ampere and the open circuit output voltage is 18 volt, because both are similar PV modules, and the two modules are connected in series, and calculate the combined open circuit voltage. I think this type of problem we have solved in the tutorial number 2. So we know that for the PV modules connected in series, either it is similar or dissimilar. You can write use this formula. Two modules, PV modules connected in series, VOC equivalent will be VOC1 plus VOC2 18.1836 volt. If in this question they have asked about this short circuit current, equivalent short circuit current, combined short circuit current, then you have to take the average IC1 plus IC2 divided by 2. And if the PV modules connected in parallel, then just this for short circuit current, just this will add up, no need to take the average. So ISC1 plus ISC2, and for this open circuit voltage VOC1 plus VOC2, take the average of the voltage, divide 2. If the n number of voltage, then it will just add it up, and you can accordingly you can take the average. So for this part the correct answer will be 36 volt B. Now let us see the 8th number question. A 3-phase 10 kVA squirrel cage induction generator is driven by a fixed pitch angle wind turbine. The generator delivers its rated power output at a wind speed of 12 meter per second. The generator is connected to an infinite bus The line to line voltage at the infinite bus is 208 volt. The generator is driven at a rated wind speed, delivering its output at a lagging power factor 0.8. Calculate the reactive power the generator needs, that is Q. For this question we have calculated, I think in the last tutorial session, active power and this current value, and here in this question we are asking about the reactive power. So this is similar type of question. You can give your answer in the chat box. So in this question, this is a very simple question. Just we have what we have given, we have lagging power factor as 0.8. so power factor is cos phi is given as 0.8. so from here you can find the sin phi 1 minus 0.64, then it comes out to be 0.6. so the reactive power will be Q is equal to S into sin phi, and we have apparent power given as 10 kVA. so 10 kVA into 0.6, that comes out to be 6 kVAr. And if you want to find this Q from using the current values, you can also find out. And then you have to write it S is equal to 3V phase I phase. From here S is given as 10 kVA and 3 into V phase line to line voltage given as 208 volts, so divide it by root 3 into I phase. From here you get the I phase as 27.76 ampere. So you can directly write S into sin phi. Otherwise you can also write it as 3V phase IV phase sin phi. From here you will also get 6 kVAr. Correct answer will be C. So now let us see the next problem. Question number 9. A stationary portion of the induction generator made up of a stack of lamination and armature is. A option is stator, B option is rotor, C option is binding, D option is all of the above. This question is part from the electrical machine. So you can see here the stationary portion. What does it mean? This is very simple problem. You can give your answer through chat box. No one is replying. This is theoretical part even. So let me give the answer for this question. So in this question it is asking about the stationary portion of the induction generator which is made up of a stack of lamination and armature. So which part of the induction generator contains this lamination part, and that is a stationary portion. So what will be the stationary? Rotor is moving part, so this option A is the only the correct. So stator will be the correct answer. Now let us see the 10th number question. A three-phase fully controlled bridge converter is feeding a load drawing a constant and ripple-free load current of 10 ampere at a firing angle of 300 degree. The approximate total harmonic distortion and the RMS value of fundamental component of input current will respectively be. So in the second problem I have given the formula that we will use in also we can use in this question. So if we see the schematic of this three-phase fully controlled bridge rectifier, it is like that. We have three controlled SCR, three legs of SCR, then in the input side we have three phase source, and we have load at this output. So each supply, each phase will conduct for how many angle? If you see each supply, or you can say each phase conducts for 240 degree, and for the constant load output current, we will get the waveform like this. Source current, and this amplitude will be I naught and minus I naught. So what will the average value for this source current? IS average will be 0, and what will be the RMS value? IS will be I naught into 2 root of 240 divided by 360. So you will get I naught into root 2 divided by 3. Now you can write the Fourier series of source current. Fourier series of source current to get the fundamental component values. So IST will be (6k plus minus 1 infinity 4 I naught divided by n pi into sine n pi divided by 3 sine n omega t minus n alpha. So from here you will get the fundamental component of source current. IS1t will be 4 I naught divided by pi sine pi by 3 sine omega t minus alpha. So what will be the RMS value of source current? Fundamental RMS value of source current IS1 4 I naught divided by pi sine pi by 3. This is the peak value, so we have to divide it by root 2. So we will get 2 root 2 pi I naught sine pi by 3 is sine 60 degree. So sine 60 is root 3 divided by 2. So we will put all these values. 2 root 2 into 10. I naught is 10 given as ripple free load current, that is, and divided by sine 60 root 3 divided by 2. So we will get as 7.79 ampere. So approximately 7.8 ampere. So we get the one value RMS value of fundamental component of input current. So we have to next calculate the TSD. For that we can find out the distortion factor. IS1 divided by IS. So put this 2 root 2 I naught divided by pi sine 60 is root 3 by 2, and then we have IS, we have calculated I naught root 2 divided by 3. So it comes out to be 3 divided by pi, and so TSD you can calculate here 1 divided by g square minus 1. So it is will be pi divided by 3 square minus 1 under root whole over. So it comes out to be 0.3108. So in percentage you can write it as 31%. If in this question they have asked about this input power factor, then how you have to calculate input power factor will be G into fundamental displacement factor. Fundamental displacement factor is cos alpha. So G is given as 3 divided by pi into cos alpha. So the correct answer is for this question number 10 is B. Now let us see the next part, next problem. If you have any doubt you can ask. So the next problem is a 3-phase diode which rectifier charges a 240 volt battery. The rectifier is given a 3-phase 230 volt supply. The current limit resistance in series with the batteries of 8 ohm. Find the average value of battery charging current. So this question is from 3-phase diode with rectifier. Three-phase diode, bridge rectifier, uncontrolled rectifier. and at the load side we have battery connected for charging purpose. So how much is the current limiting resistance given as 8 ohm, and battery voltage is given as 240 volt battery. So VB is given as 240 volt battery. So first you need to find out this V naught average. So you might be known this that what is the average output voltage for 3-phase diode rectifier. 3 VML divided by pi. And what is this VML? VML is the maximum line to line voltage, peak value of line to line voltage. Peak value of line to line voltage, or you can say line voltage. So applying KVL across this at the output of 3-phase diode rectifier, we will get the average charging current. You can take it as IV flowing through the battery. Average charging current. Average charging current IV will be V naught average minus VB divided by how much is the resistance? 8. So you will get it as IV is equal to, put these values, 3 VML. 3 VML means root 2 into VL. VL we have given as 230 volt. Always in the question we have given values line to line voltage. So 3 VML divided by pi minus VB is 240 volt divided by 8. So if you solve this, it comes out to 310.61 minus 240 divided by 8. So IV comes out to be 70.618 divided by 8. So it comes out to be 8.826 ampere. So this is the answer for this question. I think you all get this question and able to understand.
Hello, sir.
Yes.
Sir, actually, I did not attend the previous Google Meet lectures. Can I get the handouts or any PPT previous lectures you have took?
Yes, sir. For that you have to in the Swam portal, like let me show you through this Google. You can access through Swam portal. Go to the My Courses and where you have registered for this course.
I am.
And from here you can see that problem solving session. Click on this problem solving session and click here to view the problem solving session. From here you will get the presentation folder link and all the previous videos for this.
Let me check once, sir.
I think you're able to do that. You can do later.
Yes, sir. Yes, sir.
That is not a big issue.
Yes, sir. Yes, sir. Thank you, sir.
Yes.
Thank you so much, sir.
So let us see this 12th number problem. So in a buck boost converter, consider all components to be ideal. Let input voltage is 8 to 40 volt, V0 is 15 volt regulated, switching frequency is 20 kilohertz, and capacitor value is 470 microfarad. Calculate the minimum value that will converter operating in continuous conduction mode, that is CCM mode, if the output is always greater than 2 watt. This is very nice question from the power tonics. So for buck boost converter, we have this block diagram for this buck boost, schematic of this buck boost converter. We have loaded the output, so it is the inverted output here, and you can say plus minus VC plus minus VT, and this voltage plus minus VL, switching frequency, input voltage. So the input voltage varies between 8 to 40 volt. So first you have to calculate the duty ratio for the 8 volt and for 80 volt, so that you can get the boundaries duty ratio values. Accordingly, you will calculate the minimum inductance value in continuous CCM mode. So if we take input values for Vin is equal to 8 volt, output voltage is fixed, that is 15 volt regulated, that is working in closed loop. For 8 volt, we know the relation between V0 divided by V in is equal to D1 minus D. V0 is 15 volt, V in 8 volt, D1 minus D. So from here you can get the value of D as 15 divided by 23, 0.6522. Now for input voltage of 40 volt, apply the same formula, V0 divided by D1 minus D. V0 is 15 and V in is 40, so D1 minus D, so D comes out to be 3 divided by 11, so you can write it as 2.273. And for buck boost converter, what will be the ripple in inductor current? Ripple in inductor current is dV in divided by switching frequency into L value. This is the most important formula for this all for the ripple current. For all types of DC-DC converter, you should know the ripple value of inductor, and what will be the average of I inductor current, IL average. IL average you can simply here denote as IL, I naught divided by 1 minus D, and we have given here P naught. and V naught given, so you can write I naught as P naught divided by V naught. So P naught is 2, V naught is given as 15 volt. We will use it later. So we have to find out the L minimum value. You can also call it as critical inductance, so that our converter operates in continuous conduction mode. So LC or L minimum critical inductance is better to write. Minimum value of inductor for which inductor current is just continuous. Inductor current is just continuous. So if you make the waveform of the boundary value, then it comes out to be like this for inductor current. So this one is IL max. For this critical inductance, IL minimum will be 0 ampere. So this is the point. So and what will be this value? DTS, and this one is TS. And what is this height delta IL, and average of this inductor will be IL. So minimum value of inductor for with inductor current is just continuous. So what we can write, or we can write it as IL minimum is IL minimum is 0 ampere. So you can say it as IL minus delta IL2. IL minimum is that value only. If you see 0 ampere, so IL is equal to I delta IL divided by 2. And if you put this delta IL dVn 2 into Fs LC. So this is the formula for finding out this critical inductance value. Now just for these two different duty ratios, we will get the critical inductance values. So first is for duty ratio as 0.6522, and in that V in is given as 8 volt. So if you write IL is equal to I naught, so I naught divided by 1 minus D, P naught V naught 1 minus D, and we can write here dV in 0.6522 into 8 volt divided by switching frequency is given as switching frequency is 20 kilohertz. So 20 kilohertz into LC. So LC comes out to be 0.34 millihenry. And for second part, for duty ratio is equal to 0.27273, and input voltage is given as 40 volt. Just put this value. P naught is given as 2 watt, V naught is given as 15 and 1 minus D is given as 0.72727 is equal to 0.27273 into 40 V in divided by 2 into 20 kilohertz LC. So LC comes out to be 1.487 millihenry, equivalent to 1.49 millihenry. So from first and second, we are for different duty ratios we get two values. L is greater than 0.34 millihenry for duty ratio 0.65, and for second part L is greater than 1.49 millihenry for duty ratio is 0.273. So what will be the final answer? What do you think? What will be the critical inductance value for that, for the converter, such that it will never go into discontinuous conduction mode? It will always operate in continuous conduction mode. So anyone can give the reply from this to 0.34 millihenry and from 1.4 millihenry. What will be the answer? Final LC value. I want the final LC value. You can write your answer in the chat box. What do you think? Means from this value, what will the answer? So if you see that by inequalities, that L should be greater than 0.34 millihenry and L should be greater than 1.49 millihenry. So the final value will be, it should be greater than 1.49 millihenry, such that it just such that it satisfies both the equations, means L greater than 0.34 millihenry and L greater than 1.4 millihenry. So final LC value will be 1.49 millihenry. So the correct answer for this question is 1.49 millihenry. Now let us see the next problem. This problem is similar to the previous problem, but here the converter changed. In a step down converter, consider all components to be ideal. Let V naught be held, output voltage be held constant at 5 volt by controlling the switch D to ratio D. Calculate the minimum inductance L required to keep the converter is in continuous conduction mode under all conditions if V is 10 to 40 volt and switching frequency is 50 kHz and P naught is 5 watt. P naught should be greater than or equal to 5 watt. So if we see the buck converter, that is step down converter, it is telling about the buck converter. Here it is asking about the critical inductance value for the varying input voltage, and it operates in continuous conduction mode. Let us first make this schematic of buck converter. So input is V in, switch voltage across switch VT, and inductor voltage VL plus minus VC plus minus V naught. So for first let us as according to the last problem, first let us calculate the DT ratio for the varying input voltage. So for V in is equal to 10 volt, DT ratio will be V, what will be the DT ratio? dV in divided by V naught divided by V in. So output voltage we have given as 5 volt and V in 10 volt, so it comes out to be 0.5. So it comes out to be 0.5. And for input voltage of 40 volt, duty ratio will be V naught divided by V in. V naught we have 5 volt and V in is 40 volt, so duty ratio comes out to be 0.125. And since we see that for critical inductance value IL minimum will be 0, so for first part, for V in 10 volt and duty ratio given as 0.5, for finding out the critical inductance value IL minimum should be 0. So from there we can get at IL average minus delta IL divided by 2 is 0. So from here we get IL average will be this, C what will the average out inductor current is equal to I naught. So delta IL for this buck converter will be D into 1 minus D V in FSL. So you can write D1 minus D V in divided by 2 Fs LC. So from here you can also find out the I naught. I naught will be P naught divided by V naught. So we have given as minimum P naught as 5 watt and V naught is 5 volt, so it comes out to be 1 ampere. So 1 ampere, and we have given D 0.5 into 0.5, V in is given as 10 volt, and switching frequency we have given as 50 kilohertz. So switching frequency 50 kilohertz, and we can get the value of LC. So LC from this equation comes out to be 25 microhenry. From the first part, now if the duty ratio, we take the duty ratio as 0.125 for V in is equal to 40 volt and duty ratio is 0.125. So we get like similar, use the same formula, I naught is equal to D1 minus D V in divided by 2 Fs LC. So I naught you can write 1, D is 0.125, 1 minus D is 0.875, V in is 40 volt, 2 Fs, Fs switching frequency 50 kilohertz, and we can get the LC value. So LC value comes out from this part is 43.75 microhenry. So from first and second, first part says that minimum value of L should be 25 microhenry. Sorry, I am telling millihenry, it was microhenry. So minimum value of inductance should be 25 microhenry, so L should be greater than 25 microhenry. And the second part says that minimum inductor value should be 43.75 microhenry. So what do you think, what will be the final answer, final LC value, so that it will never go into the discontinuous mode and it always operates in continuous conduction mode, whether the duty ratio is 0.5, whether the duty ratio is 0.25. so it has to satisfy both the conditions. So what will the final LC value? 43.75 microhenry, so that it also satisfies the first part. So the answer for this question is 43.75 microhenry. Now let us see the next question. A sinusoidal voltage source of Vt is 100 cos 377 t volt is applied to nonlinear load, resulting in non-sinusoidal current, which is expressed in Fourier series form as It is equal to 8 plus 15 cos 377 t plus 30 degree plus 6 into cos 2 into 377 t plus 45 degree plus 2 cos 3 into 377 t plus 60 degree. Determine the power absorbed by the load. So I can just give you a hint here is that always the same frequency components will contribute to the power, real power. So accordingly you can solve this problem. So in the input voltage we can see that it only contains fundamental component. The first, there is no harmonic part, but if you see the current part, it has DC part, it has first fundamental component, and this is second harmonic component. Does anyone have doubt from the last questions we have solved? You can ask, otherwise it will just get accumulated in the last. So if you face any problem in understanding the how I am solving, then you can ask in between. And this is third harmonic part. So voltage contains only fundamental component and current contains DC component and harmonic component also. So the power absorbed by the load, the similar frequency component will only contribute to the real power. So from here you can write P load is V RMS I RMS cos phi, and it is also fundamental only because for DC there is no DC part in voltage. For second harmonic there is no second harmonic part in voltage. For third harmonic component in current there is no third harmonic voltage component in the voltage. So we will take only the fundamental part only. So VRMS1 will be 100 divided by root 2. So IRMS1 will be 15 divided by root 2. Cos phi 1 will be cos 30 degree. So 1500 divided by 2 to cos 30 is root 3 divided by 2. It comes out to 649.5 watt. Approximately you can say 650 watt. 650 watt will be the final answer. Now let us see the 15th number question. In a single phase full bridge converter, if output voltage has peak and negative average values of 325 volt and 133 volt respectively, then firing angle is in degree. This is a nice question. Only 4 participants are there. So if you see the controlled single phase controlled bridge converter, let us assume the RLE load at the output, and we have single phase source at the input. So you can write the average output denoted as V0. So you will get the V0 as 2 Vm divided by pi cos alpha for the single phase full controlled bridge converter. Cos alpha is the firing angle. Alpha is the firing angle. So if you see here, cos alpha means, like, suppose if alpha less than 90 degree, so it always V0 always comes out to be positive. So you can say V0 is always greater than 0. So you can also say that net power flow is from AC source to DC load. So this one is converter operation. Now if we have alpha greater than 90 degree, as in this question is saying that negative average value we are getting, so it means that our firing angle is always greater than 90 degrees. That's why it is getting negative average value. So V0 is less than 0. So net power flow is from DC load to AC source. DC load to AC source. So you can see that line commutated inverter operation. So what you can write now, V0 is negative, so you can write it as minus 2 Vm divided by pi cos alpha, since it is given as negative average voltage. So from here V0 we have given as 133 volt, and the peak value that is given as Vm. So minus 2 into Vm is given as 325 volt divided by pi into cos alpha. So from here you will get the alpha values as 130 degree. So Vm is the peak value of single AC voltage, AC source voltage. So the final answer will be 130 degree. Now we will bind up this session by solving this last problem. This problem is also for single phase full bridge control rectifier. So a lossless single phase full bridge control rectifier supplies a resistive load of 20 ohm for a firing angle of 60 degree. The RMS value of input current drawn from 230 volt AC supply will be. So we have a resistive load here. We have controlled single phase controlled rectifier. V in, I in, and we have output in the at the output we have resistive load of 20 ohm. You can say it as I naught. If you draw the waveform for this single phase full bridge control rectifier, you will get the output voltage for a firing angle alpha like this. This one is alpha, this one is pi plus alpha, sorry, this one is pi, and this one is pi plus alpha, and this one is 2 pi, and this one you can set omega t. So similarly you can get I naught. I naught, what will be the I naught? I naught will be V naught divided by R. So having less amplitude, then and if you want to make this I in value, then it will also go into the negative side. So it comes out to be like this. So the RMS value of I naught output voltage is same as the RMS value of input voltage. Input current. RMS value of output current is same as the RMS value of input current, as we can see from this waveform. So there is no need to find, means we can just find out the RMS value of output voltage and just divide it by R, so that we can get the RMS value of input current. So if you write the RMS of output voltage, then you can write that V naught RMS alpha to 1 divided pi alpha integration of alpha to pi Vm square. So V we have assumed as Vm sin omega t, Vm square sin square omega t d of omega t. So here you will get V naught RMS square Vm square divided by pi, so alpha to pi, so sin square omega t we can write as 1 minus cos 2 omega t divided by 2 d of omega t. So we can get at v naught rms square as vm square divided by 2 pi. So integration of constant t1 is omega t minus sine of 2 omega t divided by 2 alpha to pi. So from here we can write as v naught r square is vm square divided by 2 pi. So pi minus alpha plus sine 2 alpha divided by 2, because sine 2 pi is 0, so you can write it as like, and if you just both side under root, then you will get vm divided by root 2 into root pi minus alpha plus sine 2 alpha divided by 2 1 by 2. So put all these values. Vm we have 230 into root 2 into root 2 into root pi, and we have alpha value is given as, firing angle is given as 60 degrees, so pi minus pi by 3, so sine 120 degree divided by 2, so you will get so so you will get v naught r is 206.3 volt. So from here you will get RMS value of output current v naught r divided by r, so 206.3 volt is equal to r, how much r value is 20, then it comes out to be 10.31 ampere, 10.13 ampere, 10.13 ampere. So the RMS value of output current is same as the RMS value of input current. You can write it I in R is equal to I naught R 10.13 ampere. So the final answer for this problem is 10.13 ampere. So that is all for this today's session. If you have any query regarding any parts of this, any part of question we have solved today, and also from the last assignment, last tutorials we have solved, you can ask. Hello.
Sir, thank you, sir. So you explained very well. I understand very neatly. So simple way you explained, sir. Okay. So
Thanks.
thank you very much.
Thank you, Rama.
Sir,
Okay.
good evening, sir.
Yes.
Sir, I have one question on last assignment, sir.
Last.
Last assignment.
Okay, last assignment.
Yeah. Sir, in that you asked one question regarding the which among one is called a traditional controller. In that option, we have given that machine learning based controller and PI controller.
Yes.
Actually, machine learning based control is latest one traditional, sir, but the answer is PI controller. That is my question.
Yes. Your
So
voice.
actually nowadays we have yes, sir. Nowadays we have the many many optimization techniques based on the machine learning is available.
Yeah.
Sir, am I? But then that you given the answer is PI controller is called traditional controller. That is my question, sir.
So all these machine learning artificial neural networks, what means if you see these types of controllers, these are newly controllers, and PI controllers already developed have been very means was we are using from very what you can say so
So
many years
actually,
back. These all are
okay,
intelligent controllers. If you see that machine learning, ANN, fuzzy logic, these are all intelligent controllers. We can use that controllers for optimization and many all those things. So
sir, but
means if you compare all these controllers, what do you think? PI controller is they don't have. We have to do traditional controller. We have used to tuning. We have to find the KP and KI values, and
yes,
they
sir.
don't have brain. Means like,
Okay, 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 sir. Thank you, sir.
uh, and anyone else? If we don't,
Okay, nothing, sir. Okay, nothing, sir.
okay, thanks. So we will meet
Okay,
in the next week at the same time. Thank you all for joining, and have a good day. Have a nice
okay,
weekend. Okay, thanks.
okay,
Bye
sir.
bye.
Thank you. Thank you. Bye, sir.